increase in frequency. Why I think that this is true. This would happen. We use this in astronomy. What's funny, though, is you can calculate how fast you'd have to be coming together for this to ever happen. How much that frequency shifts. You'd have to be going at relativistic speeds. And then you have other issues, let alone the fact that you've probably ran into everything else along the way because you're going way too fast.
Why is it that it's like a blue shift and not a purple? That would have a higher.
Excellent question. Thinking man's question. It could be called a purple shift because purple would be even more. I don't know because I didn't come up with a name. So they call it a blue shift. But it's a good point. Because its waves are even smaller. Purple's even smaller than blue and vibrates even faster. It's on the very edge of our visible spectrum. Red's on the other end. Blue's on this end, but purple's even further. So his point is, well, it might have been better to call it a purple shift, which would be accurate, but they didn't, and I don't know why. Oh, right. You know, we're getting to there. We're getting to that. So, in theory, if you start going fast and you start increasing your speed more and more and more, first this would get shifted to orange, because that's a little higher frequency, then yellow, then green, then blue, and if you go even faster, purple. If you go even faster, it's now in the ultraviolet. You wouldn't even see it. So it depends on the relative speed between you, which is what is true with the Doppler effect, sound or light. The greater that relative motion, the greater the shift. But anyway, I thought you'd enjoy that. Oh, see, I talked long enough. Screensaver. Problem is, when it's connected to the projector, it always takes forever to come off a screensaver. So let's just speed things up. Get your clickers out. I got a couple questions for you then. All right. Now you can see the numbers. I'll get the questions I chose. And there's the first one. So, we talked about the speed of sound traveling through different things. Which one does it travel the fastest through in this example? See what you remember or can reason. In the next couple chapters, we'll talk about the speed of light and how it can change through different things, because it's a wave. But right now, we're on sound. Ten, 9, 8, 7. Nobody's yelling at me, so 6, 5, 4, 3, 2, 1, 0. 37 of you. 76 steel. Good. Steel is the only one of these that's a solid. We got liquid as water and gas as air. And sound travels faster through solids. Why? It's more elastic, so the vibrations can transfer faster. And what did you say? Yeah, I always felt it's more dense. They're closer together. Bottom line is that both of those mean there'll be more interactions because they're closer together, which makes it more elastic and is the reason it's more dense. But yeah. So think interactions when you're thinking of the speed of sound through something. In air, they're really far apart. So it'll bump this one, but it might take a while before it gets to this one. So it just delays it. Questions? Yeah. Thank you.
Does the time it takes for the
Oh, that's a good question too. So something's vibrating at a certain frequency, doink, and he hits a neighboring molecule, transfers kinetic energy and momentum, and this one bumps into this one. And we're not talking about the speed of the molecule, but the speed of sound through the medium. And so, in a sense, the speed of sound is kind of like an average as it goes across. Or think of those rods where I move them and the pulse goes by, or our slinky thing. The springs themselves kind of speed up and slow down. This one gets sped up, oh, and then it could slow down, and then it hits this one and speeds up back this way. They just go back and forth, or up and down. And we're not talking about that speed of the individual molecules, but the speed of the wave, which is consistent through the medium. But it's kind of like an average because microscopically it's doing other things. And I say all that because remember all that. It becomes more important with light when we get there. Because light does not need a medium to travel through. It can propagate all on its own. So if it's going through something like glass or water, it has to interact with the medium. And that's going to affect its speed. Or at least the time it takes to get through it. All right. The speed of sound varies with which of these? In other words, which of these, if it changes, A, B, C, or D, will make the speed of sound change? Your caveat is, you know A, B, C, or D, they can all change. But what affects the speed of sound? Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Meh. Most of you C, and that is correct. Here we'll read what the author said. Although loudness varies with amplitude, and pitch varies with frequency, I haven't talked about pitch specifically. Pitch is, as the book defines, is kind of subjective. It's what you hear, but it's based on frequency. So if I play a certain frequency chord, you hear that note, but you call it pitch. That can be a little more subjective. But if you change the frequency, it's going to change the pitch you hear. But how fast something vibrates, it can vibrate like this, or it can vibrate like this, doesn't change how fast it travels through a medium. Just how much they're wiggling, bumping into each other. Next, speed is not influenced by those. And here's his example. A listener in the back row at a concert would find music confusing if sound of different frequencies reach the ear at different times. I like that example. Because if high frequencies traveled faster, let's say, then in the back row you'd hear all those notes before the lower notes, and they wouldn't be in sync, and it would sound like a big garbled mess. So that can help you remember that frequency doesn't affect speed. And that's true for all waves. Again, sound and light. Questions? So why does temperature change it? Right, it changes the medium, and thus those interactions. Good. Hello, wrong button. And I didn't do that one yet. Okay, there we are. Dang it. I'm done with clickers, not with my laptop. All right. So let's talk about how these waves kind of bounce around. Waves can reflect. We've done that back and forth to create standing waves, but they can reflect off of materials, echoes, reverberation. This is, the law of reflections is nice and easy. Do you want to do it, Brenda? Because you're superhero and used this. You can come up and teach it if you want. She learned all about this. First of all, let's say this is air, and this is a wall. Then a wave comes in, and we can think of the wave fronts like this. But it's easier and faster. They're moving in this direction. So we're just going to draw a ray representing the direction of velocity of the wave. You with me? That comes in, and it's here. Well, it reflects back. But at what angle? It goes in and out at the exact same angle. That's the law of reflections. You can think of it as like throwing a ball. And then it bounces up. It's going to come in and out the same angle. Now with a ball, you can put English or spin on something and change things. But you can't put English on a wave. We use a term to help you. We explain things. A normal. We've seen that before with normal force. It's perpendicular to the surface. And so we say this angle, Greek letter theta, is the angle of incidence. It's the angle of the incident ray that's coming in. And this is the angle of reflection. It's always with respect to that normal. And for the law of reflection, they're always the same. So that tells us where sound's going to go, in what direction, where it'll end up. Same with light. If we want to know how something bounces off of a mirror, we can figure it out exactly. Pretty straightforward. So if you go into the field of acoustics and you want to design an orchestral hall, what are things you're going to have to deal with or worry about? What was that? You have dead spots for interference, yeah? And you probably don't want dead spots, or do you? All right, what if you got rid of every dead spot? How would it sound? You'd think it'd sound really great. But the sound just keeps bouncing and bouncing and bouncing, and it might seem garbled. That's kind of like when something reverberates too much. It's like, hello, no, no. But they keep playing, and that's blah, 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 yeah, yeah, yeah. That can be annoying for a concert hall, too. So they have these chambers, anechoic chambers, where every substance is baffled. The material absorbs the sound, or the angle of it bounces it off so that it gets absorbed. And they design those very specifically using the law of reflections to make no sound reflect. There's no reverberation at all. It sounds really freaky. Even like this, I don't hear myself echo, but I get a little feedback. When you're in one of those, it's just completely dead. It's weird. We're not used to that. But on the flip side, you've gone in a room. How many sing in the shower? All those hard surfaces close by, that's kind of the reverberation. And that can be fun for singing by yourself in the shower, but not in a concert hall. So they balance this, and they make material. So like in this room actually used to be more echoey. They refurnished it a couple summers ago, and there's carpet that more absorbs the sound waves. These hard surfaces bounce them off. The brick bounces them off. But the tile absorbs them. And the angle, the step of it, if it's coming in at a certain angle, it might get more trapped. And so it's less likely to at least bounce around the whole room. You've probably been in halls where you've seen some funky looking shapes and angles. Half of it's design, but mostly it's functional. To balance a good amount of reverberation and dead spots. Absorption. And so there's the whole careers on that.
You've been in one of those rooms where they have the things that absorb all the sound?
Yeah, that's the anechoic chamber where it's completely dead. Have you?
I haven't.
Yeah, it's freaky. They're good. They have one at BYU, I know. And they're handy for when you want to test things, but you don't want all those echoes messing up your data. You want it just from the, that's what they usually use them for. Now, another way is refraction. This is when the waves change mediums. If it can actually go into a second material and travel through it, that's refraction. This is just bouncing off of something and, it all comes back. So again, we have a surface, let's say air, and how about water? We know sound travels through water, so does light. And so you have an incident wave coming in. We draw our normal. Here's our angle of incidence. And there will be some of that wave that reflects. At what angle? This angle. But all of it doesn't reflect off of water. A lot of it goes into water. And it doesn't go straight. It changes properties as it goes through the water. This is that idea, because the time it takes to go through water is different. And so it bends. And it'll end up refracting. And we measure with respect to the, we'll call that 2, I guess, angle of refraction. Refraction is the bending of light. It's not like the light really bends, it just changes directions. And I have a sort of demonstration for this, the way to think of it. Here's wheels on some axles. They spin really nice. They roll down like this. Sorry, can you guys see over there? Gravity. So think of this as a wave crest moving forward, causing the medium to start vibrating. It's fine here. Here's cork. Goes a little slower because there's more friction. I don't know if you can tell. Whoops. But what happens if some of the wave comes in and part of the wave's traveling in this medium, air, and part of the wave is traveling in this medium, say water, where it travels at a different speed? What will happen? You got it. Maybe I let go of it wrong, so let me repeat. It bends, changes directions. In this case, this travels more slowly in this medium than over here. So this one goes faster, this one goes slower, and the wave crest, the wave front, the direction of the beam, the wave changes. If you prefer, think of how many of you like going mudding with your 4x4, or just normal car. You're on pavement and then you get stuck in mud. Same idea. You can come in from this one and watch. We're headed that way. Gets to there and it still kind of turns a little. Again. Hits it and redirects. Yeah?
Does this work for all types of waves? I think
yes.
You mentioned light, but does it also work for things like
Sound
sound?
is a wave, light's all waves. This works for all waves, yes. Water waves, pressure waves, longitudinal, transverse.
So what do you mean on the board when you have like the circle?
Oh, we could call this theta 1, angle of incidence. This is theta of reflection, but it's the same as 1. Theta 2 is a different angle than theta 1. Just to emphasize, it got bent. So this would be theta 1. And it's not that. And the reverse is true too. If it's coming, the reverse of this case, say it's coming back up. If this is the incident ray, here's our angle of incidence. Some of it reflects back down into the water. But it won't go straight. It'll refract. Other way. In this case, because we're going in the other direction. If it's going to slow down in one direction, it speeds up going the opposite way. Point is, it gets bent. We call that refraction. Right, Brenda? Our eyes do that. When light goes from air into our eye, it changes mediums, and it bends. Sound does the same thing. Okay. Now, I like this animation showing a little more how this is useful. Snell's Law, I'm not bringing here, but Brenda studied it, so I'll write it down. I'm not holding you to this, but this index of refraction, which is the speed of the wave compared to the speed of sound. Well, let's just make it easy. For sound, this would be the speed of sound. If it was light, it'd be the just do this. No, that's not right. Do this. The speed in the medium versus the speed of the wave. I'm being so generic here. If this was sound, this would be the speed of sound in air. But then when it goes into water, it's a different speed. If it was light, speed of light, it's fixed. But it'll travel a different speed through water, for example. This is just a ratio to give you an idea of how fast it's moving. The sine of one angle and the sine of the other. And so you could actually figure out exactly the angle it bends by this law. Some of you might be interested in that. That's a very useful law. And by the way, Richard Ingebretson is somehow related to this Snell, last name of a scientist. I don't remember how, but he's proud of that. So let me show this animation. There it is. Make it big. There's a principle of least times. So you can use Snell's law to figure out this angle, but it makes sense conceptually. That's what I'm going to do now. So here's like a lifeguard sees somebody, help, help, I'm drowning. So the lifeguard sees, and most of us, the shortest distance between 2 points is a straight line. So he runs straight for the person. Let's see how long that takes. He's on the sand where he can run faster. Then he gets in the water and he can't swim as fast. So his velocity slows down. And it'll tell us how long that took in this simulation. There it is, 11.641. Well, what we're saying here is, well, what if we let's make it shorter in the sand where we go faster. We're already going fast there, so let's make it the least amount of distance. Great. Oops. But now we're spending way too much time in the water. A lot farther distance where we don't go as fast. I think you can see already this is not as good. So these waves did take the path that will require the least amount of time. You can think of them as like smart little demons that can figure it all out at an instant and know where to go. But well, what if we did the opposite? Now this makes sense. Let's spend the most time where we can go the fastest, most distance, and then short there. That makes sense. So we do that. Boink. All right. Now we're going slower, but we have a lot less distance to cover. And this is faster than the last couple, but there's an optimal time. Because even though that idea is right, this is farther than we need to go. We've increased the distance a lot. It works out, I believe. I don't know, let's try that. Now, we're still most of our time where we go faster and slower. overall, woo, that would take the least amount of time at those angles. This describes it, Snell's law, and it tells us exactly how much it bends. Again, all because the wave fronts travel at different speeds in the different mediums. And so part of the one half can travel more slowly than the other, and it's forced to bend. Now, does that make sense? Because we're going to be bending waves going forward here. All right. I should mention, if this wave bends, do you think the sound changes pitch? If you hear a note, let's say 440 hertz in the air, and you go underwater, will it still sound like 440 hertz? What do you think? Have you ever tried to listen to your radio and then while you're swimming, but when you're underwater? Sure, it gets quieter, but you can still hear it because sound travels through water. Does the radio sound different? It sounds muffled, but that's the amplitude. Does all of a sudden the sounds sound like chipmunks? Or demonic? No, I'm singing down here. No, that tells you the frequency doesn't change. The wave is still trying to vibrate at the same rate. So what must be changing? We're hearing the same thing, so the frequency is not changing. The waves are still vibrating at the same rate. We've just discussed that the speed changes when it changes mediums. So if it goes faster, what's that mean? Humor me, tell me. The wavelength has to increase. Yeah. So if it was, if the wave looked like this, and it goes into a medium where it now can travel faster. So you can think of that as going this way, from the slower one into the faster one. Then the speed changes, but it's vibrating the same. That's fixed. So this has to change. If that goes up, this goes up. And if we have a bigger wavelength, yeah, that would be something like, and I'll exaggerate, because now this wavelength is that distance. This wavelength is that distance. So it's increased because it's now traveling faster. Or vice versa if we go the other way. Bottom line here is when the wave frequency doesn't change just because it changes mediums. It's still trying to vibrate at the same rate. It's just now going through something different. So think of, the air molecules. It's trying to vibrate them. And now tries to vibrate the water molecules. It's still trying to vibrate them at the same rate. But it takes longer for that wave to transmit through it because of all those interactions. Said that wrong for sound. Sound would actually speeds up in water. Light actually slows down, but I haven't explained why yet. So sound goes faster in water than air. Let me reiterate. We'll learn that light actually slows down in water compared to air. Questions? Whoops. Okay. Let's do... doing well. All right. All these vibrations and getting through things, and they have kinetic energy. Remember that a wave is a way to transmit the energy of these vibrations and to get energy from me to you. That's how you can hear the sound. But energy can get used up. Total energy is conserved. So if it's in the form, the energy is in the wave, it could dissipate and convert to some other form. It's doing all these interactions. Where do you think the most likely form of energy, the sound energy or wave energy, can go? Any ideas? It's trying to make all these things vibrate and move around. You know, as the wave passes me, it might make me go, whoa, and then I'll come back. I'm done. But it's moved over to here. And it makes this one, whoa, and they're hitting each other, rubbing up against each other, bumping into each other. Lots of interactions. I was hoping somebody might be able to guess. Get your thinking, get the squirrel moving a little faster. Let you think. No ideas? How about when we start moving things? Here, we'll use this. I'll relate it. I got it moving. Newton's first law says it should keep moving forever, right? But it doesn't. Why? Friction. Well, that happens molecularly, atomically too. Microscopically, I could say. And what does friction convert that heat to? Heat! Yeah. Thermal energy. All this motion, you know, fine, but as you start moving, they bump and rub into each other. Yeah, you can convert a lot of that energy to thermal energy, heat. And that happens with waves when they go through things. They can lose some of their energy. You know this because I go, hello, and you hear me. But if you get further away, at some point you won't hear me anymore. Why not? Doesn't the wave just keep going? Why does it stop? Because that energy gets absorbed, or as you can think of it, it's dissipated away from the wave. And it mostly goes into thermal energy because it's making all these things vibrate. So sound can travel farther through some materials than others because some materials dissipate the energy more quickly. Air, and we can use that railroad train example. You know, you might not be able to hear the train quite far away because it gets dissipated through the air. But it could be miles away, and you could probably hear it through the solid metal rail. It doesn't get dissipated as much in that case. Usually, all else things the same. Thermal energy, then, let's see. Which frequencies will dissipate more quickly? Slower, why? Why? Why would they want to run out of energy faster? Because they're not moving as fast in the first place? There's some logic there. Any other votes? Who thinks high? I'd like to hear a reason for that one. Okay, why? See, rural life experience, she's going off yeah, that's a good example. So you're saying, like at a stoplight, and you're hearing the annoying bass notes, but yeah, you don't hear all the high frequencies? Now, why don't we hear those high ones? Is that this reason? Any other thoughts? Yeah. Oh, I didn't think of that one. So if I whisper, you guys can still hear me okay? Yeah, okay. All right, but it probably sounds a little higher. It's kind of hard to whisper low, too, but I could try to talk this one. I don't think you can hear me. Well, there's two real-life cases, common experience, that are leaning towards the high. We've got 2-to-1 votes. Anything else? Well, in this case, common experience does win. Those two are correct, and it has to do with this. They're being driven, but they're going at a certain speed. The key is the interactions again. If something is a higher frequency, it's trying to vibrate them more quickly. So that's like going like this. And I'm going to create more thermal energy They can be dissipated away. Then if I'm going like this. So it was good logic, but that's why slower loses less energy with time and distance. They just have less interactions. But the faster gets them vibrating more, and they just more energy to go to thermal. Thus, high frequencies generally don't did I just contradict myself? I did. In my mind I did. We'll justify. So high frequencies generally dissipate faster. So the car example works straight out. They get dissipated and we just hear the lower frequencies, longer wavelengths. Whispering. Well, there isn't the bass really to get filtered out. We're talking higher. I thought of another thing to justify that. So why would whispering want to use higher frequencies? If they get dissipated? That's true. We usually whisper when we're close. That's one reason. I mean, you wouldn't be able to hear this very far away. Let's go back to our range of hearing. I didn't specify it. The frequency response of our ear is not uniform. In other words, we hear from 20 hertz to 20,000 hertz. Okay, you guys did. Around 3,000, 3,500 hertz, it peaks. So if you don't change the loudness, the amplitude of the wave, but you just change the frequency, when you get around 3,000 to 4,000 hertz, it sounds louder to us, the way our ears are physiologically built. A whisper approaches those frequencies more. It raises the frequency where our ears are more responsive. Our ears just naturally hear that range of frequencies better than really low notes. That's another reason, probably more to the point why we hear the whisper. But, so high frequencies don't go as far. That's why they have foghorns. Longer waves, lower frequencies won't dissipate as fast. They can make it farther out to sea to help save some ships. So if you want somebody to hear you really far away, yeah, make it loud as possible, but a lower frequency should travel further. Yeah.
So is that because there's less wavelengths, like since high frequency goes through more wavelengths faster, that's why it fades out?
Yeah, you can think of it that way. A higher frequency does go through more wavelengths faster. That means the frequency is higher. Yeah, it gets from here to here more quickly than here to here. Remember, the point is just going, that's one cycle, one wavelength. The wave is traveling. It has to cover more distance on a longer wavelength, lower frequency. Yeah. I have a video for you. This is our author. I don't know, have any of you ever looked anything up on his? Listened to him? I love this example too, and I usually explain it myself, but I thought, to show you him, let's listen to him. This has to do with sound traveling and refracting and bending. It's kind of cute. Wait till the screen stops making noise.
Sure, sound will travel a little faster in a warm day than a cold day. And let me give you some evidence of that.
We did that. The speed of sound increased in warm air. It's 340 meters per second at room temperature. It's only 330 at cold. Again, the interactions. They're moving faster, so they interact more. It travels faster.
It's something that occurred to me when I was a kid. I couldn't figure it out. And later on, when I got into physics, boom, the answer to my question came. When I was a kid, I used to be a Boy Scout. And we used to go camping up at Camp 9 in Saugus, Massachusetts. And we'd camp on one side of the lake. This is a lake. And there'd be another scout troop over here. And we'd have our tent set up here. And we'd tent out here. There's our troop here. Here's that troop over here. They've got their tents. In the daytime, you could yell up and go, hey, guys, how you doing? can't hear you. How you doing? Fine, how you doing? Okay. How's it going? Oh, you know, these heavy conversations you have, yeah? But it turns out we could just barely hear each other. But at nighttime, you could hear these guys whispering in the tents. You could hear them so clearly. I can remember that. And I wonder, well, at nighttime I can hear those guys. How come I can hear them so good at nighttime? In daytime I can't. And I didn't know the answer to that. And it took me a long time to find the answer to that. Has anyone ever experienced something like that? It's not all the time true, but under special conditions, sometimes you can hear a lot clearer from a long distance than other times. Let me tell you what happened. Okay? It turns out that over here, let's suppose over here, someone says, hello, how are you? And we get sound waves coming out like this. And the sound keeps going. Now it turns out the direction of sound will always be at right angles to the waves. For example, like this. Like that. Right angle, right angle, right angle. See that? So when all the air has the same temperature, then the sound will travel at equal speeds in all directions and form all these circles, yeah? But how about in the case where maybe at nighttime it's relatively cool above the water and relatively warm above the so-called temperature inversion? When that happens, how about this one? Will this wave get to here, or will it turn it on? In the warm air, it would get to here. In the cold air, it would get to here. And up here, maybe, to here. So you know what's going to happen to the wave again? The wave is going to be bent more like that. When it gets over here like this. Now, my rays being perpendicular up here. Ooh. Look at that. See that? Okay. So what you're doing is you're getting more energy in the air at nighttime than you want to say, because the sound is being bent. The waves are being bent. We don't say waves bend because one part's going faster than another. We have a name for that. What's it called again? Refraction.
Cool, huh? Practical application. Question. He does a good job with explaining stuff.
In our last 4 minutes, I want to do this one. Here's two speakers, and they're facing this way, and I'm going to drive them. They're going to push, 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 and they're going to increase the pressure in the chambers. There's 3 holes here. When they go this way, they'll increase the pressure and air will blow out. Then when they come back, they'll blow out here. So it's going to go poof, 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 poof. And I can set that frequency of the speakers and that driving with this function generator. And I can make this vibrate. So I'm driving it. I have a driving frequency. This piece of glass naturally wants to vibrate and set up a standing wave. Here's the 2 nodes. You can see it's not moving there, but it's moving here and here. And go a little more. So we have a standing wave. So I'm driving it, forcing it to vibrate at its natural frequency, and when that happens, you have resonance. To help you see that, I have a laser I can bounce off of the end here that's moving a lot. And let's dim the lights just slightly so you can see this. Over here up on the brick wall, let's say. There it is. So here's what happens if I adjust the volume. Here's what happens if I change the frequency that I'm driving it with. See, I'm not driving it at the frequency it naturally wants to resonate, so we didn't get as much energy put in. We didn't hit resonance. Now I'm going to go the other way with the frequency. Keep going. A little further. If you care, I'm actually increasing the frequency. Keep going. Oh yeah, we're getting closer to resonance. Oh, now it's getting smaller. So I'll back up. Actually, we'll go higher. Now I'm going to increase the amplitude. Not much happens. Let's go back to the resonant frequency. Somewhere around here-ish, I think, was good. All right, now that we're on resonance, it doesn't take as much energy to put into it. It wants to vibrate this way, so it's easier. Now I'll up the amplitude. Oops. And that's exactly what's supposed to happen for this demonstration. We put so much energy into it because it was easier at resonance. It wanted to vibrate there. It broke. That's like the opera singers, shattering a wine glass. That can happen. This won't take long. I won't keep you. This is simple. Here's my driving frequency. The spring naturally wants to vibrate at this frequency. So if I drive it at that frequency, the amplitude increases. We get more energy into the wave. It gets louder. It gets brighter. And just like the glass over there broke, yeah, this can actually fall apart. You can change it. If I change the mass by adding a little more mass on, it now has a different natural frequency. So for that same driving, okay, it's getting good. It's getting good. Oh, wait a minute. Now it's getting smaller. They're kind of effectively canceling each other out because they're out of phase. And then for a while, they get back in phase. Oh, this is good, this is good. But then they get out of phase. And so this one never is off resonance. But we're creating beats. That's what beats is. It's waves interfering. And sometimes they're in phase, and then they get out of phase. And then in phase and out of phase. And you hear that kind of, if this was sound, you'd hear it, wah, 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 wah. And I'll do a demo of that Monday, but I'll stop. Your papers you can turn in down here, your hard copies, and I hope you guys have a great weekend.